Welcome. The title of today's notes worksheet is Derivatives. This lesson is simply a continuation of the previous lesson dealing with the tangent to a curve. So we can just expand on a few ideas and do some examples together and just get a little more practice with it. So let's go ahead and start with example 1. I have a nice looking quadratic function there, and what we'll go ahead and do is find the derivative of that function and then utilize that derivative in a couple different ways. So let's start it out here. If you remember yesterday, we talked about the derivative as f prime of x, and it is the limit as h goes to 0 of f of x plus h minus f of x all over h. So if I look at it within this function right here, f of x plus h means very simply put x plus h into the inputs of this function, or replace the x's with x plus h. It's another way to look at it. And so instead of x squared, it's x plus h squared. Instead of x, it's x plus h. And then I've got the plus 1 on the back. So that's f of x plus h right there. Then we've got our big minus right here. I like parentheses on the back because now we basically just say, all right, let's go ahead and put x back into the function. So there's your x squared plus x plus 1. And all of that, of course, is over h. And that looks really nice. We've got that piece. And now it is up to us to work with that expression and then see what we can do in terms of taking the limit as h goes to 0. So let's go ahead and see. I've got the limit as h goes to 0. At this stage, everybody, we should be fairly confident being able to expand that. That would be x plus h times x plus h, which of course is this piece right here. Remove the parentheses, not that it was a big deal on this one, so plus x plus h plus the 1, and remove the parentheses on the back, minus x squared, minus x, minus 1, all that over h. All right, it's time to play a little slash and burn here, everybody. X squareds, x's, 1's, they're all gone. And that simplifies things a little bit here. I'm going to probably do this in a couple different steps. I definitely have the room to do it. So I have at this stage 2xh plus h squared plus h all over h. And remember, what we're looking to do based on our properties of limits is let h go to 0. And we want to plug 0 in for h, but I can't at this stage. Obviously, I have that major dilemma in the denominator. So I'm going to wait, I'm going to wait, I'm going to wait until I can pull the trigger on it. So let's see what I can do. Just careful on this. In order to get rid of that h on the bottom, I do have to factor the h from the top. So let's see what we end up getting. I've got the limit as h goes to 0. Let's pull out an h from each and every term. Got that right there. Don't forget the plus 1 on the back. H times 1 would give us this h right here. Good. Now it can go. There they go. I'm going to rewrite it one more time and then let it happen. So I've got the limit as h goes to 0 of 2x plus h plus the 1. All right. Now, if you're at that stage, you're in very good shape, because what we're looking to do is let h go to 0. And I guess I would ask you, can we let h go to 0 now without any mathematical repercussions? You bet. Of course we can. So let's let h go to 0. And so we put in 0 for h right there. And then we are left, once we do that, this goes away, because we are now taking the limit as h goes to 0. And so when it goes to 0, that's what I'm left with. And guys, of course, that's your derivative. All right. Excellent. We found the derivative of the function. Now what we want to be able to do is utilize that. And I guess we should develop a little meaning behind that. Remember, the derivative of the function would be the slope of the tangent line at any point on the graph of the function. So now let's get somewhat particular with this. And let's go ahead and do parts B and C. Which, by the way, actually, you know what? Let's connect B and D. That's what I see going together. And then C and E go together. If you want to go ahead and utilize it that way, that's fine. So what I'm thinking, of course, is letter B says, find the slope of the tangent line through 1, 3. So 1, 3 is a point on the graph of the function. If I want the slope of the tangent line at that point, I have it. Now you'll have to excuse me here. I have to write my derivative up. You have it obviously on your paper. I just don't have it on the screen, but I think we got 2x plus 1. And remember how nice this is, everyone. All I have to do is put in the x value into the derivative, because this expression right here gives me the slope of the tangent line at any single point. And so in this case, very simply, I'm going to do 2 times 1 plus 1. So again, one more time on that. Sorry for the redundancy. But the derivative is the slope of the tangent line at any point. And so if I have my x value for my point, I put that in. 2 times 1 plus 1 is 3. And there you go. There's the slope of the tangent line right there. Obviously, it changes based on the point. And so in this case, find the slope of the tangent line through a different point. So negative 3 comma 7, well, all I have to do is use that negative 3, and negative 3 goes into the derivative. And I should get negative 5 as a result. Theoretically, everyone, could I put any of the infinite number of points on the graph of the function in place, and could you tell me the slope of the tangent line? Yeah, of course. And that's the point of the derivative. Now, one more step with this. After finding the slope of the tangent line at that point, what do you say we write the equation of the tangent line at that point? And so let's go ahead and do this piece right here. Now, of course, I'm going to actually write the equation of the line. And this goes back a little ways, but nice and simple. This is at least how I do it. Slope of a line, or I should say the equation of a line, is just y equals mx plus b. And I have all the necessary ingredients to go ahead and put this together and find my equation. I have the slope already, right? So let's go ahead and connect. So in this case, the slope of that tangent line was 3. I got that by putting the 1 into the derivative. Got the slope of the tangent line. And of course, everybody, let's go ahead and put this. Here's your x and here's your y. So I'm going to use them. There we go. So 3 there. Y is 3. And then plus b. So 1 goes in for x, 3 goes in for y, and it allows us obviously to solve for the b. And I'm hoping you see that the b value would be 0 there. Now as a result, hey, we've got this. The equation of the tangent line at that point should just be y equals 3x. Could I do the same thing for any particular point on the graph of the function? Of course, and I just put a couple. So how about this point right here? There's your negative 3 comma 7. I found the slope of the tangent line. Could I now find the equation of the tangent line? Yeah, of course. And it's, again, it's just algebra 1. Given a slope, given a point, can we find the y-intercept and hence the equation? This is going to be 15, by the way. So I'll go ahead and take this in 2 steps just to make sure we catch it. Subtract 15, and I'm getting 7 minus 15, which seems to be negative 8. And so as a result, we get y equals negative 5x, and how about minus 8? Excellent. So I did it for just 2 arbitrary points on the graph of the function. But again, theoretically, could I do it for the infinite number of points on the graph of the function? Yeah, I mean, of course. And that's the idea behind that derivative. Hey, let's just check this out. I'm curious myself. Let's go see. And it might not be the best window for it, but just drop pencils for a sec and just take a look. You don't have to type this in, but it'd be interesting to see nonetheless. So guys, here's our function. Let's talk about that initially. Here's our function, and I'm going to hit zoom in number 6, and there it is, just a nice parabola. And remember, the derivative would give us the slope of the tangent line at any single point. So I picked 1 point. Here's 1 comma 3. Does everyone see that right there? 1 comma 3. So picture, of course, the slope of the tangent line, or picture the tangent line, I should say. Slope of the tangent line apparently was 3. And the equation of that tangent line should be y equals 3x. Let's take a look at that. So I'm going to go back and type in 3x. And again, it might not be perfect here because of our window. But does it look like that is the tangent line at that particular point at 1 comma 3? Absolutely. Without question, that looks really quite good. Now let's see that other point that I had. Here's another point on the graph of the function, negative 3, 7. Let's see, here we go, guys. 1, 2, 3, up 7. So it's about here, give or take. And so in this case, everyone, it looks like I've got a tangent line looking like this. Everyone see that? Negative slope, because it's a declining line. And let's go ahead and type that one in. I'm curious how good it is. So negative 5x, throw in the minus 8. Is it a winner? Yeah. I mean, it's not great here. It's getting a little convoluted on my screen. I don't want to play around with it too much. But again, the idea is, could you find the equation of a tangent line for any particular point on the graph of the function? Absolutely. Cool. Let's try maybe just one more function with this, get a little practice on that. And again, just same deal. So example 2. It would be honestly great if you could pause the video and see if you could pull this off just on your own here. The only thing that makes this really a little harder is that 3 out in front of the x squared. So see if you can find this derivative. Good little practice on it. I'm going to have to come up here a little bit. So first and foremost, f prime of x equals, limit as h goes to 0. And guys, make it happen. I know you can pull it off. So here I go. I'm going to maybe shortchange it a little bit here, just a little. But again, I hope maybe you're paused at this stage or not. Anyway, let's go for it. F of x plus h. So take those x's and replace them with x plus h. So I have that and that minus f of x. So let's go ahead and let x revert back in. And so I just get this piece right here. And all of that over h. So hopefully you can see that on your screen. I'm a little high up on mine. But now let's make it work, everyone. So I have the limit as h goes to 0. Here's the key, guys. We're able to do this when you remove the parentheses. Should be able to square x plus h, then multiply each one of those by 3. And if you do that, removing those parentheses, you get a 3x squared, you get 6xh, and you get 3h squared. If you didn't quite get that, please call me over so we can look at it. And then minus 4x minus 4h plus the 1 minus 3x squared plus 4x minus the 1. All over h. All right, so it's a little intricate at this point. Let's start cleaning it up. Say goodbye to the 3x squareds, the 4x's, and the 1's. All right, so I'm in pretty good shape right now. Notice the top is really starting to clean out a little bit. And again, you probably know where this is headed, so I'll ask you to pull this off. I'm going to take the limit as h goes to 0. And I'm going to pull out an h from those 3 terms remaining. I think I could do this at this stage. So pull out the h minus the 4. And that's all over h. These h's are going to go. And now, guys, once the h's go, am I able to finally pull this out? Am I able to take the limit as h goes to 0? Yes, I definitely can. So it is time to let h go to 0. And when h goes to 0, this middle term disappears. 3 times 0 goes away, and I get 6x minus 4. And so long story short, I'm hoping you're able to get this derivative as well, but there we have it. What is the derivative of a function? Well, basically for our purposes at this stage, it gives us the slope of the tangent line at any single point on the graph of the function. So in this particular case, if I have 2, 5 on the graph of the function, I want to know the slope of the tangent line at this one point right here. Hey, let's just take that x and put it in. So I do exactly that. It would kind of look like this just in terms of our notation. F prime of 2. I'm letting 2 go in for the x value of the derivative, f prime of 2. So 6 times 2 minus the 4. And it gives me 8. So there's the slope of the tangent line at that particular point. That looks great. Could I then take it one step further and not only talk about the slope of the tangent line, but also the equation of the tangent line? Sure. And so just this is the way I pull it off. I let the slope is 8. That's what obviously we found in part B. And now I have my x and my y that I utilize. So I've got that right there, and let's go ahead and get B. And so as a result, I get 5 equals 16 plus the B, and B is negative 11. So we're in pretty good shape right here. I think we have it. Y equals, and what do we say, 8x on that, and then minus 11. So you've gotten a couple practice problems under your belt at this stage. Finding the derivative, then finding the slope of the tangent line at a particular point, then finding the equation of the tangent line at a particular point. Once you get past the derivative, I think this is all pretty much Algebra 1 and Algebra 2 mathematics. And I know you can pull that off. Wonderful. All right, well, let's move forward here, get to that next stage. And this is an extremely cursory summary of what you've been working on with slope over the last few years, but oh, it is what it is. So here's what I wrote, just the summary. Slope. Since Algebra 1, you've talked about slope, and to make a very long story short, when you talk about slope, you're really talking about the rate at which something changes. So slope is always the rate of change. Always has been, always will be. Now from first semester in Pre-Calc 1, we talked about what is called the slope of a secant line. And that would be between any 2 points on the graph of a function. And as a matter of fact, the title of the notes worksheets when we did exactly this, when we found the slope of the secant line, was what we called the average rate of change. So kind of underline that piece, if you would, the average rate of change. That would be how the function is changing between any 2 points on the graph of the function. And this happened to be the formula that we used. It is just slope. y2 minus y1, just in function notation, over x2 minus x1. Again, just using the inputs and outputs. That was definitely from Pre-Calc 1. Now, obviously, guys, what we're referring to in this particular unit is not how a function changes between 2 points on the graph, but literally how a function is changing at a single point. And that, of course, refers to the slope of the tangent line. And as it says, at 1 point on the graph of the function, and it represents for us in an application context not the average rate of change, but the instantaneous rate of change. So how something is changing at a single moment or at a single point. Instantaneous rate of change. Okay, so pretty nice, huh? Let's go ahead and utilize it with one more problem. So example 3. A diver jumps from a platform diving board that is 32 feet above the water. The position of the diver is given by the model right here. All right, so guys, let's box this up. Nice and easy. Position in terms of time. And so what we're going to do here is kind of go back to first semester for just a moment and kind of pull this off. So part A would be average rate of change because we're talking about between 2 moments in time. So from 1 second to 1.5 seconds, on average, how fast is the diver going? So average velocity. And so we're going to go ahead and do that. Then we'll transition into what we would call the instantaneous velocity, the instantaneous rate of change. So it's good. I like this one. We get to see kind of both parts in action. All right. Now, just as a reminder, just in terms of what part A would look like, one more time, this is the average velocity or the average rate of change, and it's just slope. So what we're going to do is make a little fraction line. And very simply, what we're going to do is x2 minus x1 down on the bottom. Let's do the easy one first. So again, average rate of change, x2 minus x1. Inputs being subtracted. So I would say we're going to subtract 1.5 seconds minus the 1 second. Okay. Now, Here's the only dilemma that we saw first semester when we did average rate of change. We didn't really have the y values. They weren't given. So all I know is if this is the input, we have to come up with the output. We have to come up with the y value. So we have to come up with the position at 1.5 seconds. We also have to come up with the position of the diver, the y value, so to speak, the function value, at 1 second. And so that's what it's going to look like. S of 1.5 minus S of 1 over 1.5 minus 1. All right. Well, not too bad. I think we can kind of let the calculator do some of the work here. I'm going to need those top numbers. So I'm going to take 1.5, put it back in. Then I'm going to take 1, and I'm going to put it back in. Let's do it. Here we go. So back to my main screen right there. And I have negative 16 times 1.5 squared, and then plus 16 times 1.5, and then plus 32. And I end up getting a position of 20 feet. All right, I'll keep that in mind, and then get the other one here. Let's take care of that. So what about 1 second? So negative 16 times 1 squared plus 16 times the 1, and then plus the 32. And I get 32. So my two positions, my two y values, would be 20 and 32. So let's do that. 20 minus 32 over 1.5 minus 1. All right, not too bad, right? This is just slope. y2 minus y1 over x2 minus x1. And in this particular case, 20 minus 32 would be negative 12. 1.5 minus 1 would be 0.5, and that's looking great. If you want to grab a calculator here, you're more than welcome to. Negative 12 divided by 0.5 should be negative 24. And let's develop at least a little context for this. What would be the units for this particular value? Think about the top. That was in the position of the diver, the change in the position, I should say, when we did 20 minus 32. And you could see that would be in feet. So the position is measured in feet. And the time, which is the bottom, is measured in seconds. And so lo and behold, you have an average velocity of 24 feet per second going down, hence the negative. Now, does that mean on this particular interval that the diver is constantly traveling 24 feet per second downward? No. All this says is on average, that's the velocity of the diver. So it doesn't mean all the way through that time interval, he or she is traveling this particular velocity. It just means on average from here to here, he or she is traveling 24 feet per second down. Okay, that's average rate of change. Nice, good measurement. I like it. Now let's transition. It does say we're going to use B. We're going to use B here to get C. So it just says determine when the diver will hit the water. And it kind of just says plug 0 in for S of t and solve for t. So the diver goes up, comes down, and is going to hit the water. The position of the diver is 0 when he or she hits the water. So I'm going to let that work right there. And as a matter of fact, I'm going to just go ahead and use my wonderful quadratic formula program. And you can write this on here as well to solve for t. So theoretically, we should be talking about factoring and completing the square and all that great stuff. But you know what? No, let's not. Let's just use the quadratic formula, and I want to know what t is equal to. So guys, I bring up my calculator. You hopefully have it on yours. If you do not have the quadratic formula program, that's okay. Please just ask. I'm happy to give it to you. You probably will need it before the end of this unit. So guys, let's go ahead and do this. I'm going to hit program, and I've got it right there. There's my quadratic formula program. So I'm going to hit enter one more time. And A is negative 16. B is going to be 16. And C is going to be 32. All right, now I got two values here. I'm going to write both of them down. It seems kind of silly, but it looks like t is equal to -1 and t is equal to 2, which does tell me, by the way, we could have probably factored this and solved, but that's all right. This was better. Now, obviously, guys, it says determine when the diver will hit the water. It can't hit the water at 2 different time periods. And I guess this one doesn't really make a whole lot of sense, right? The diver's not going to hit the water at -1 second. So in this particular case, even though this works in the equation, it just doesn't make a whole lot of sense. So I think this, guys, is your winner. The diver hits the water at exactly 2 seconds. Is everyone okay with that piece? So diver goes up, comes on down, and literally at the moment of impact on the water, according to this model, it would be at exactly 2 seconds. So let's use it. One last piece. So it says given, and guys, box, I was kind on this one. I gave you the derivative of this model right up here. So here's your function. Remember, the position function of the diver. Here, guys, is the derivative of that function, s prime of t. All right, now it says, what is the velocity of the diver when he or she hits that water? Okay, so what we're talking about here is not the average velocity between 2 moments in time, but literally the instantaneous velocity at a single moment of time. So at the moment of impact, how fast is the diver traveling? And we use the derivative to get that. And that's what it says at the top, everyone. So very simply, we know the diver hits the water at exactly 2 seconds. So that is our x value, so to speak, our input. So we literally just put that into the derivative. -32 times 2 plus 16. And when you do that, you end up getting -48. And here we go, guys, feet per second. So look at part A and look at part C, and we'll start to round this out here and conclude it. Part A was what we would call the average velocity. And again, that's 2 moments, 2 values on the graph of the function. What makes the derivative, and this so interesting, and in my opinion mathematically powerful, is we're talking about how fast the diver is traveling at a single moment in time. At exactly 2 seconds, the diver is traveling 48 feet per second downward. There you go. So if we have our derivative, very simply the instantaneous rate of change at any particular point is the value of that derivative for a given input. Okay, I hope that makes pretty good sense there. Please, again, if I need to clarify or elaborate on anything, don't hesitate to ask. But it's looking pretty good. Well, thanks for listening, and let me know if you have some issues to talk about.